So now that we know how to write an augmented matrix, now the question is, how do we actually then solve this system? How do I go back and find x, y, and z? Which there's a lot of steps involved in this process. So I'll return to the packet and I'll walk through what we refer to as the elementary row operations. But essentially, it's a way of progressing through and simplifying our matrix down to triangular form, which is something I mentioned earlier. But I wanted to revisit, why is triangular form useful? But like, if we think about a general system of equations that looks like this right here, the problem is I don't really know x, y, or z. I don't know anything because each equation has not been simplified. I have not eliminated any of the variables. And my first goal in solving this would be to, well, I could eliminate x by adding these equations together. I could eliminate z by adding these equations together. And in so doing, I could set up a series of steps where I've eliminated variables in the proper order, as we did in 3.4, to actually finding the answer I wanted. But if I look at a system that's presented in triangular form instead, notice the value of this is that a system in triangular form has very little math to do to actually solve, because the last equation, and notice it's in triangular form because it's got the triangle of zeros in it as well, which is something I referred to with matrices before. But it's kind of like if I was to write this as an augmented matrix, I would have 1, -2, -1, 1. 0, 1, 2, 5, 0, 0, 1, 3. But I would have this triangle of zeros. I can't make a triangle here, but you can kind of imagine that there's this triangle of zeros and a triangle of numbers, which is in upper triangular form, versus lower triangular form, which would have all of these up here be zeros. Well, technically either one is useful, but with augmented systems, you always want upper triangular form. Anyways, well, so again, why is this useful? Notice that why it's useful is that z has already been solved, right? What it says is z is equal to 3. And if I know that z is 3, I could plug in z right there, which would be 6, and subtract 6 the other side, and really y should follow from there. And once I know y, I could plug in y and z into this equation and go back and find x. But basically, a system in triangular form is already solved for me. There's really no hard lifting to do. It's a matter of backsubbing as well. And if you return back to when we solved systems before, our goal was to eliminate variables. Like, say, for example, I add equations 1 and 2 together like that. What would happen is I would get, well, 0, y, plus 2z equal 5. And really, I could generate these simpler equations by adding these ones together. That's exactly how we did this. But what I could imagine is taking, if these were matrices, I could take the two rows of the matrices, add those together, and that would give me a new row. And the goal of adding these rows together would be to formulate new rows that have zeros in the right places. Because if it's in triangular form, it is practically solved. And so after saying all that, that's really the goal of solving a system. But the final goal of a system is to not just get into triangular form, but to get it in such a form which looks like this. Because if I look at this matrix, what it says is that x, again, if this is assuming this started from an augmented matrix, this is that x plus 0y plus 0z is equal to 3. But notice this says x equal 3. This says 0x plus 1y plus 0z equal minus 5. Really, that equation, if it's in augmented form, says y equal 5 minus 5. And this one, like exactly triangular form here, 0, 0, 1, 3, tells me z is equal to 3, or in this case, z is equal to 7. But basically, the value of this matrix is it is solved, right? I can read the answers to the system from it. And we often refer to this as reduced row echelon form, which is just kind of the name for a system being solved, where when it's in triangular form, it's sometimes referred to as row echelon form. But basically, these are forms that tell us that something is nice. And really, the way that we get a matrix into row echelon form or reduced row echelon form is by doing the same thing we would do to systems, adding equations together, forming an elimination. But when we're in a matrix form, we have very specific rules which are referred to as the elementary row operations. But how I remember them personally, because the concept of what we're doing is we are using the elimination strategy to solve an equation. Basically, we're going to add this equation to this equation to generate a new equation. Like I said before, it's kind of like I'm going to add equations 1 and 2. That gives me equation 4, a new equation. I could say, for example, I could also add equations 2 and 3 together to eliminate x again, giving me equation 5. And it's like I'm generating new equations in order to simplify the system and eliminate variables. And the elimination of those variables allows me to solve that system. But basically, let's go ahead and read what the elementary row operations entail. And then in the next video, I'll do an example of solving a system the old-fashioned way, i.e. via elimination, and then using the elementary row operations and kind of comparing and contrasting what's going on as we're doing it. But basically, if you want to take an augmented matrix, like in the last video, we took a system and we rewrote an element. We rewrote it in augmented form. But basically, if you perform the elementary row operations on this matrix in a sensible way, you can solve the system if you try to get it into that reduced row echelon form. And this is not a concept that is usually taught in one class period. So we're getting into, this is all referred to as what we call linear algebra, which is a course that a lot of math majors or engineering majors have to take just as a study of matrices and the mathematics in general, which we're kind of doing a quick crash course in these videos. So and we're not going to get into the more advanced topics on matrices, just kind of scratch the surface of the usefulness of matrices in general. But basically, the goal is to take an augmented matrix like this one and get it into reduced row echelon form, i.e. like if we apply these rules, we can solve the system by getting it into this form. And what the elementary row operations say we can do is operation number 1, you can add a multiple of one row to another. So basically, I could take, like say I was trying to solve this system right here. I could add this row to this row, which would give me a new row, and that could help me solve it. And technically, you can add any row to any other row you want, but the reason I would choose, say, these two rows is because if I was to add this one and this one, that would produce 0. And the value of 0 is it's an elimination of the variables, which is just like the strategy that I taught you guys, right? We're trying to eliminate the variables so that I can get rid of 2 of the variables and get z by itself by combining the equations together. And so really when I'm adding rows together, that's the same thing as adding 2 equations together. And we want to do it very strategically so that we get zeros within our matrix. And really the goal is to get zeros in each of these places so that we're solving it in an organized fashion. You can also multiply a row by a non-zero constant, which would be, say I wanted to take this row of this matrix and multiply through by 3. That's another thing I'm allowed to do. And why I would want to do that is, well, say I wanted to add row 1 and row 3 together. The problem is there would be no elimination of variables in these rows, right? Because if I add 3 with minus 1, it's not going to make 0, it's going to make 2. But if I were to first multiply this by 3, that would give me negative 3, 0, 12, 33. When I then add that to row 1, now it would eliminate and it would present me with a 0. And again, 0 is like the goal. I'm trying to make zeros so that I'm eliminating my variables. And the third elementary row operation is you're always allowed to interchange 2 rows. So like if I want to switch this equation with this equation and switch them from row 1 to row 2, I'm allowed to do that. It's just like in this system of equations, the order that they're in doesn't matter, right? Equation 1, 2, 3 was all arbitrary. I could switch where they're at. It doesn't really matter. But the other thing I wanted to bring up in this is that when we're using the elementary row operations, we're not really, this is not matrix math. We're using a matrix to specifically solve a system of equations. It's not a normal matrix procedure. It's a specialized procedure designed to help us solve systems and work with augmented matrices. So all of this math is very, very different than in the last few videos when we were talking about adding and multiplying matrices. It's just kind of different because it's serving a particular purpose. And in your packet, there's a detailed description of what does row echelon and reduced row echelon form look like, and the strategy that goes into actually solving this. But in the next video, I'm going to actually do an example of solving a system via matrix method and compare it to the elimination method that we did back in chapter 3. And ultimately, there's a lot of strategy and a lot of steps in solving these, but the goal is to, one, simplify this process of solving systems, and two, put it in such a way that a computer could actually recreate our steps and do it programmatically. And then once we kind of get into the how of why this all works, well, then I'll teach you how you can actually solve systems in your calculator by using these sort of commands.